All right, welcome back. This is part two of section 8.1. We finished up part one of this by talking about the reality of hypothesis testing and how we're going to make mistakes. Mistakes are going to happen. There are two types of mistakes that can happen, a type 1 error and a type 2 error. A type 1 error is when the null is rejected, but we shouldn't have because the null was true. A type 2 error is when the null is not rejected, when it was false, and we should have rejected it. Okay? All right, so let's take a look at what that means. Here is our example where we're going to be asked to identify what those things are in this scenario. That is, here's a scenario. What does it mean? All right, so the USDA has a limit for salmonella contamination for ground beef, and it's set at 7.5%. A meat inspector reports that the ground beef produced by a company exceeds the USDA limit. You perform a hypothesis test to determine whether the meat inspector's claim is true. Okay? So our claim is the thing that was said by the meat inspector. So our claim here is that the proportion was greater than 7.5%. The meat inspector claims that the beef produced exceeds the USDA limit. Exceeds means it's more than. Not that it's equal to, not that it's less than, that it's more than. So we're writing that as a mathematical statement, a greater than. Since our claim doesn't include an equal sign, our claim is going to be the alternate hypothesis in our pair of hypotheses. Is that the proportion is greater than 0.075. Our null then would be that it's not. Okay. So we're going to go gather some data and we're going to run a test, right? If we run the test and make a type 1 error when we run the test, what does that mean? Well, let's see. A type 1 error is when you reject the null hypothesis, but you shouldn't have because it was true. Now, if the null hypothesis was true here, then the meat was safe to eat because the null hypothesis says that since it's the complement, the amount of salmonella is 7.5% or less. That's what our null hypothesis is saying. And so a type 1 error is we reject that. We say that it isn't safe to eat when it actually was. So a type 1 error, essentially, we are having a hard time writing today. We're throwing out good meat with a type 1 error. Because the type 1 error, we say the meat's bad when it was actually good. Right? What's a type 2 error here? Okay. Well, a type 2 error, that's where we fail to reject. Type 2 error is when we don't reject, we fail to reject, but the null hypothesis was false. So a type 2 error, the test said the meat's good because it fails to reject the null hypothesis, but the reality is the meat was bad. So a type 2 error means that we are going to eat bad meat. Right? A type 1 error occurs when we say the meat is bad when the meat was actually good. A type 2 error is when we say the meat is good when the meat was actually bad. Which one's worse here? Would you rather throw out some good meat or eat some bad meat? Now, I think we could all probably agree that in this specific scenario, the type 2 error has more potential downside. Someone could get potentially very ill if they contracted salmonella by eating bad meat. So in this case, a type 2 error is worse. That does not mean that type 2 errors are always the bad ones. Errors are bad, period. In this scenario, you would hope that the test that the ground beef inspector does tries to make this one as small as possible, a small error rate. But like I said before in the first video, if I make type 2 small, it unfortunately makes type 1s larger. And so it would be more common, more likely to make a type 1 error then. But again, if type 1 is we happen to throw out some good meat, and type 2 is we're eating bad meat, I'd rather risk throwing out some good meat to reduce the amount of times I eat bad meat. Okay? All right, so that's what type 1 and type 2 errors. There is no way to say which one's the worst one. You have to look at it claim by claim by claim. Right? All right, the significance level of your test. The significance level of a hypothesis test is the maximum allowable probability for a type 1 error. Almost always designated or denoted by that alpha, the Greek letter alpha. It looks like an A, kinda. Depending on who's writing it, you'll sometimes see it more fishy, stretched out like that. It really shouldn't be that horizontally stretched. It should be a little less, right? But it kind of looks like a fish or something. I don't know. It's the Greek letter alpha, right? We set alphas to small values, saying that we want to reject a true null at a small rate. Commonly used levels of significance are a 10% level of significance, a 5% level of significance, and a 1% level of significance. Okay? That type 2 error is designated as beta. Right? Now, we are going to be doing alpha level hypothesis testing. Alpha level hypothesis testing means that we are going to test, and this value is going to help us determine whether we do or do not reject that null hypothesis. We do alpha testing. There is something called beta testing, where you work your test off of that Greek letter beta. We don't do that here at this level in this course. Right? So we do alpha level testing. There is something called beta level testing. It's outside the scope of our course. If you end up taking further stats at some point in your career, you might run into it. Okay, so how do we test? Well, this is the process. We read the statement and find the claim and use it to define our pair of hypotheses. Once we've got our hypotheses, we assign an appropriate level of significance, whether it be the 0.1, the 0.05, or the 0.01. Then we go gather data, and then we test our data. Right? We're going to find something called the p-value for the data, and we are going to say that whenever the p is less than or equal to alpha, we reject that null hypothesis, and whenever p is greater than alpha, we fail to reject the null hypothesis. Now, if you're wondering about the math that's going on here, here's the math behind the scenes, right? Everything we're going to be doing is going to be based off of either a normal distribution or a t distribution in this chapter. And so we're going to have this normal or this t distribution, and they look a lot alike. The middle of that is going to represent our claimed value. Right? And I am going to draw this example out based on the following pair of hypotheses. That the mu is less than some claimed value, some number, or that the mu is equal to some claimed number. Right? Now, before the test is run, we are going to assign a level of significance. That is that 10% or that 5% or that 1%. That value of alpha is going to determine the size of our rejection region. Okay? So this number right here is referred to as our critical value. That critical value splits our distribution into two pieces, where this piece right here, this left tail in this example, has an area that is exactly alpha. So if you're running a 10% level of significance, that tail would have an area of 10%. If you're running a 5%, that tail would have an area of 5% of the distribution. 1%, 1% for that area. Or if you want to think about things in terms of probability, that tail would represent a 10% chance. That tail would represent a 5% or a 1%. Then we're going to go gather data. And that data is going to give us sample information. That data is going to give us a sample mean and a sample standard deviation. Right? We're going to take that data and we're going to plot that data on this horizontal axis. And if that data plots anywhere to the right of that critical value, this is going to be the fail to reject region. So if X bar ends up plotting there, or if X bar plots there, or if X bar plots there, if our sample data plots anywhere over there, we're going to say the data's close enough to the claimed value that we can't reject it as true. If our data plots over here, anywhere in that tail, if our X bar plots over there anywhere, that's called the rejection region. And if it plots over there, we would reject the null hypothesis. We would say that, hey, you said it was this. Our data is over here. Our data is significantly far enough away from your claim that we can say that the data does not support that null hypothesis, that claimed value. So when I run my hypothesis test, the math is going to give me a decision. It's going to say either you reject or you fail to reject that null hypothesis. That's the math answer. So these are the math answers or the math solutions. Now what we then interpret that to mean is one of these four statements here. One of these four statements over here. Those four statements are the actual answer to the hypothesis test. If the math tells us to reject the null hypothesis, so if the math says do this, and the claim was the null, then the answer to the problem would be, hey, you claimed equality. The data said to reject that, so there is sufficient evidence to reject the claim. If the math said reject the null hypothesis and the claim was the alternative, we would say there is sufficient evidence to support the claim because we're rejecting the null. Right? What if the math says don't reject, fail to reject? Well, if the claim was the null, then we would say there is not enough evidence to reject the claim. We don't say the claim is true. We say we couldn't find enough evidence to prove it's false. All right. If the math says to reject the null hypothesis and the claim is the alternative, then we would say there is not enough evidence to support the claim. Okay. So these four statements here are going to represent every solution that we make, every final answer that we make to a hypothesis test. Okay. Now the question we should have at this point is, how do I know when the math tells me this, reject, and how do I know when the math tells me that, fail to reject? Well, when we run the test is going to return and give you something called the p-value. This is the output from our test. Okay? The output from the test is a p-value. If the p-value is less than or equal to alpha, we reject the null hypothesis. If the p-value is greater than alpha, we fail to reject the null hypothesis. The easiest way to remember is, if the p is low, the null must go. And I'm not a big fan of sing-songy things like that, but it works here. If the p-value is low, meaning less than alpha, we reject the null. The null must go. Okay. All right, let's move on a little bit here. That brings us to the end of section 8.1. So in section 8.1, the whole goal here was just to lay out the basic idea of what's going on. This is the basic idea of what's going on. Okay. Now this picture that I drew here, the rejection region was this left tail because the alternate hypothesis was a less than statement, often called a left tail test. If I swap some things here, like if I make this be a greater than, now the rejection region isn't over here. The rejection region would be over here because the alternate is a greater than, or that would be a right tail test, and we would get our critical value being over here on the right. If our alternate hypothesis was the not equal to, that's referred to as a two-tail test, and we would get two rejection regions, one on the left and one on the right. Now when we have a two-tail test, the size of the rejection region would end up being half of the level of significance. What I mean by that is, in a two-tail test, if there's a 10% level of significance, the left tail is 5% and the right tail is 5%. That way we get 10% rejection region. If it was 5%, then over here on the left, this one would be 2.5%. This one would be 2.5%. That way both tails add up to our 5%. Similarly, if it was 1%, each tail would be 0.5%. So 0.5% plus 0.5% will give us our 1%. Right? All right. In section 8.2, we're actually going to run hypothesis tests from start to finish. Hopefully, if you're a little bit fuzzy on it still, that'll clear things up. So anyway, have a great day. I'll see you all back here for 8.2.